Hi, Phil.
Hi.
How are you?
Hey, good to see you, Tatanka. How you
So,
doing?
so, we are here today for your talk, and this is our group. And
Great.
one of our professors is also here, Professor Sriparna Saha.
Hi, how you doing? Nice to meet you all.
So this is our group, and we are eager to listen to you. And so I will just read out your introduction, and then you may start.
Okay, thank you very much.
So Phil Gooch has been building text processing and automated knowledge extraction solutions for the publishing, education, legal, and healthcare sectors since the early 90s. Phil has a PhD in health informatics from City University London, and prior to founding Scholarcy, Phil led to the development of natural language processing solutions at Babylon Health. So today, Phil would be discussing about his awesome AI-powered summarization engine of scientific articles, which is Scholarcy. So yes, Phil, you may start.
Thank you very much, Tatanka, and thank you for inviting me to talk to you. It's a real honour, so thank you very much. I'm going to share my screen and show some slides, and we'll do a bit of screen sharing and demos and stuff as well. So, great. Can you see the slide there?
Yes. Yes. Yes, Phil.
Great.
Yeah.
Okay. So I've called this is about creating rich representations of scholarly articles, with the aim of supporting a number of processes, not just for students or researchers to be able to quickly gain the main points from an article, but also some of this technology could hopefully help things like peer review and manuscript screening at the submission stage, when somebody's submitting an article to a journal or to a preprint server. So we'll look at some different use cases for some of this technology as well. So as Tirthankar said in the introduction, I've been working on natural language processing solutions for a while, but I wouldn't consider myself an expert in the latest deep learning and neural approaches to summarization. But my background is more on sort of more traditional machine learning and linguistic approaches to natural language processing. So I tend to combine rule-based and statistical approaches in the tools that I've built so far. I'm starting to look into some of the neural approaches. So I'm sure many of you know more about this than me, and maybe we can have an interesting discussion about how these approaches can be combined in future. So just an overview of what we're going to cover. So just talk about what were the goals of Scholarcy and summarizing scholarly and scientific articles, and then how the engine was built, and then looking at how we take a document and turn it into machine readable data, and then we'll look at different approaches to summarization, and then we can have questions and discussions. And feel free to interrupt me anytime if anything you'd like clarification on, or if you've got a point you'd like to raise, happy to be interrupted, so don't be shy. The motivations for building Scholarcy were that, well, when I was doing my PhD myself, and this was about 9 years ago now, there was nothing out there that would actually help me understand an article from the point of view of being new to a subject. So, I was researching papers on clinical guideline models and process mining and process modeling. And I was reading the literature, and it took me a while to get up to speed with it. And discovering the papers wasn't a problem. I knew how to search, and I knew how to find papers, but it was obviously then I downloaded, several hundred papers, and I had to read them. And this was, the time-consuming part. And the abstract isn't always enough. It doesn't always tell you enough about the paper to know whether you need to invest the time in reading the whole thing. So I needed something that was something between the abstract and the full paper that would give me like the main points, the main findings, and figure out, can I trust the findings, and how can I check whether what they're saying is correct. So that was kind of the motivation for building it. But that was, I was doing my PhD 9 years ago, and there was nothing out there for doing this kind of stuff. And then I forgot about the problem, and after doing my PhD, I worked for a couple of different startups. I was at Mendeley for a couple of years. And then, as Tirthankar said, I was at Babylon Health. And it wasn't until beginning of last year that I thought, actually, I'm in a position to maybe build something now to do this, because I'd learned enough about engineering as well as the NLP side to actually try to put together a tool that would do something like this. And by this point, beginning of 2018, there was lots of discovery tools, even more than there were when I was doing my PhD. So we've got tools like Dimensions, and we've obviously got ResearchGate and Mendeley and academia, and we've got new tools like Meta, and we've got Science Open. There's lots of tools for discovering papers, but there still isn't really anything that will actually summarize them to the point of getting the main findings and really sort of helping you kind of follow links and understand, what the paper's really talking about. Certainly from a new reader's point of view, I think that's still true. And they're the people who tend to be the customers of Scholarcy, because I did end up spinning it out as a company. And so Scholarcy is now how I pay my bills and put food on the tables. But originally it started off as a side project. So what do we mean by enabling improved understanding? So, for example, this is the output from Scholarcy on a particular paper. So it's taken the PDF and it's chunked it into these sections. And what's it done here? It's for somebody who doesn't know what the terminology means, such as IRBD, it expands that into the term isolated rapid eye movement sleep behavior disorder. And there's actually a hyperlink there that will take you to the Wikipedia article about it. So, you can get some background knowledge about what this is about. Unfortunately, we can't do the same for GBA. In this paper, they never actually define what GBA means. It assumes you know what that is. So, that's a disambiguation problem. There's no easy way of knowing what GBA refers to in this case. So there's some limitations here. We can't always expand these abbreviations if they're not fully spelled out somewhere else in the text. But it's helpful for most of the time that they are. We can do that. And so, if you're reading this in isolation in the discussion, because quite often when you read a paper, you won't read it in a linear way. You won't start at the top and read it all the way to the end. You'll tend to dip in and out of sections, won't you? You may read the abstract first, then you might go straight to the discussion and conclusion, and then you might go and read the methods. So you're not always going to read it from top to bottom. And so one of the ideas here is that we can go straight to the discussion by clicking on the tab and expanding that. And so you might then think, well, what's AAO in this context? And so having that expansion here of these terms is quite useful. And then, you've got references in the paper, and this is a preprint, which means that it was originally just written in Word and uploaded as a PDF file. So none of these numbers were clickable. None of these numbers were linked to their citation. So the other thing that Scholarcy does was to link these to the actual citation here, and then actually find that paper and then summarize it. So we actually get a mini summary of the paper that's referenced here, so we can see what were the main findings of reference number 15. And that's quite useful because it actually lets us fact check what the author of who's citing number 15 is saying, and is this true? Was the sample size quite small? We can see there was 69. There were 69 patients. So yeah, it was quite a small sample compared to this study. I can't remember how many participants in the study that I'm currently reading here, but there was 69 in the one that they're citing. So that's true. So they were citing this correctly. So you can see there's two components here, and this was the things that I built first in Scholarcy, is the expanding abbreviations and pulling out the references. So that was, summarization actually wasn't originally part of the plan. It was really just terminology extraction, keywords, abbreviations, and references. And the summarization stuff came later. But that was one of the motivation factors, is being able to quickly dive into a paper and see and fact check it and do the terminology. So that's one of the things that drove it. And the other thing was, if you do have some of these things in place, then you can actually then use it to improve discoverability. So although I said that there's lots of discoverability tools out there, and that wasn't my motivating factor, after all this, you can actually say, well, actually, if we have snippets and keywords and summaries of papers, we can actually feed that back to improve search and discovery. And here's an example. I've removed the branding from this, so I won't tell you which search engine or publication this comes from, but you can see I did a search on Alzheimer's and tau protein, and I get some search results, which is great. But as in most academic search engines, when you get your search results, you just get the title, list of matching titles and the authors, and then you've got to click. And then you've got to click on the title and read the abstract and decide, is this relevant or not? So you've got a lot of screening before you even download anything when you're searching through. So what if, instead, your search results contain snippets of the main findings of each paper? That might be quite useful, mightn't it? Certainly I would find it useful anyway. So actually seeing in this paper here, what did they do? What did they investigate and what did they find? And in the second one here, what did they introduce, and what are they proposing? You know, so what were the main things that this paper is talking about? Now, sometimes the title is enough. You don't actually need this. So in the first example, actually the title of this paper, this deficiency increases tau phosphorylation without causing deficits. So the title actually is quite descriptive of what they've actually found. But in the second example, reverse engineering a signaling network using alternative inputs, that doesn't really tell me anything about what they found or what they've done. So having a micro abstract or a micro summary that goes into a bit more detail could be useful. And similarly in the third result, what they actually did and what they've actually shown could be useful there. So this is a way of enriching search results with a short summary. But that wasn't my main motivating factor, but it was just something I thought, well, having built this stuff, can we actually then feed it back into Discovery to improve that? So that's one potential use case. So in building this tool that breaks down research papers into their key components and summarizes them and finds keywords and links the references and everything, these were the tools that we used. So I wasn't doing any primary research into, you know, extending the state of the art of NLP here. It was just really an engineering problem. But from the point of view of, you know, your own research that you do in your institute, you know, you might have a view to thinking, well, how do we productionize this? How do we turn this into a service or a product? So what I was doing was taking some tools like Scholarcy, which you may be familiar with, which is an NLP kind of set of NLP tools for doing things like dependency parsing and classification, and it's wrapped up into some nice APIs that you can use and train your own models. Snorkel, which is something I'll come on to in a bit, which is a way of bootstrapping rule-based approaches to build a machine learning model. And then Text-to-See is a library that sits on top of Scholarcy that adds some extra things like different keyword algorithms and relation extraction, things like that. GenSim has some useful ways of training topic models and has some has a summarization engine built into it. And then on the engineering side, Flask lets you wrap your code into a nice API. And then you can see there's multiple technologies involved here. So it's not just Python, it uses Ruby. So a parser for parsing references. This is an open source tool which I modified and retrained. And then C++, using modified versions of tools like PDF to text, PDF images, and PDF figures. I put my modified version of PDF figures on GitHub, which you can access. PDF figures is a way of extracting figures from scientific articles, where some of the other tools like PDF images, which is part of the Poplar package. I don't know if you've ever done any PDF parsing or used any of the PDF tools, but there's a tool called Poplar, which has a tool called PDF images, which is useful for extracting bitmap images, but it doesn't do so well if the images or the figures contain line drawings in them as well. So PDF figures tries to do a better job of that. So there's a number of technologies involved, some of which, I'll say, on the Scholarcy side involve creating new models, GenSim, and then others were really just wrapping this up. So what are we trying to achieve here? In the introduction or in the abstract I sent for this talk, many of the NLP tools or NLP research looks at small chunks of data, don't they? They maybe look at summarizing news articles, which might be quite short. They might be, 1,000 words long in the original article, or they might be, classifying the sentiment of a review, a movie review, which again might be quite short or might only be a paragraph. But for the sort of stuff in the real world, you've got documents that might be 10, 20 pages long, so they might be 15,000 words, 20,000 words, or they could be 200 pages long, they could be 100,000 words. How do we actually deal with documents of this size? And so one of the things, the first step really is just to get the text out of the document. And so here's the original paper. Here's the text that comes out using a tool called PDF to text, as I mentioned earlier, using this library called Poplar. And you can see there's some cleanup that's going to be required here, because you've got like A's and 1s after the name of the author. The abstract heading doesn't actually appear near the abstract. The abstract appears afterwards. You can see the abstract heading has come out here, and then you've got like the article history and received and accepted dates, and then finally you've got the abstract. And then you've got some keywords supplied by the author, and then you can see that I've got the heading introduction. But this is just plain text. We don't know this is a heading, right? We don't know that one.introduction is the start of where the real body of the text appears. We've got all this stuff beforehand, haven't we? We've got to find a way of classifying this. So one of the first things to build was a classifier that goes through each line of the text and classifies it as, is it just noise? Do we not care about it? Is it a title? Is it the authors? Is it an affiliation? Is it the abstract? And then is it a section? So that's the next thing. I don't know how big your screen is here, whether you can see this or if it's really small. Is this visible here, that the information I'm showing you on the slide? Can you see this JSON data?
No, I guess it is not that much visible, but I guess we'll have the PPT presentation, so we may have a look later.
Okay. I mean, let's do this for real, right? Why not? So so you can see. So I'm going to take a paper. Can you see this paper here? I've got just published on bioRxiv. So let's put it into the API. And run through. I've no idea how this will come out. This paper's just been published this morning on bioRxiv, so I don't know what the results will be like. So right, is that better? Can you see that?
Yes.
Yeah.
Yes.
So you can see some of the information. So this is basically what it's done. It turned that document into text, and then it's classified each item. So it's figured out the title, the date, the author, DOI, the abstract, and then the references haven't come out quite successfully. There's a few gaps here, but you can see it's tried to pull out the references, and we've got other things like the captions, the sections, just the snippets of the sections, the default, and then you've got all the structure of the article and everything here. So basically this is what it's done. It's turned that document into data. But behind all that, what's happening is, as I say, it's just pulling out the text, and then it's classifying each item and then turning it into this machine interpretable format. Here's another example with the Word document. Do the same thing. Pull out the text, classify each line, and then turn that into structured data. And once you've done that, then the problem is a bit more tractable, because I'll delete, so I close that one now. Because then you can decide, well, which parts are we interested in? We're not really interested in extracting keywords from the captions particularly, are we? Or maybe even the references. And the references could be quite long. And we might say, well, we're not interested in anything after the references, so we might ignore the appendix, for example, if there is one. So we might just then focus our attention on the area between the abstract and the references, and just focus on maybe summarizing that. Or maybe we just want to summarize individual sections. Now we can chunk the text into sections. We might just then say, well, I'm going to summarize the the introduction, the methods, and the discussion and conclusion. You might decide that, and then you've got a smaller amount of text to work with. So let's look at, as we've talked about summarization, let's just look at a few approaches to it. Now, I'm sure from the research that you're doing, I think some of you are doing summarization, and you're probably looking at neural sequence-based models or transformer models. And these kind of are awesome. And some of these models generate, these generative models are really amazing now, aren't they? Using some of the techniques from BERT and GPT-2, and they generate text that is grammatically correct and syntactically consistent. But where they really fall down is that they're often factually completely wrong, and you can't really tell. You can't really tell the model to attend to facts easily, can you? And so here's an example. So the summary starts off okay, but then as it goes on, it starts going off on a tangent. Now, the paper that this is a summary of doesn't mention ADHD at all. It's all about cognitive impairment in Parkinson's disease. But as this neural generated abstract goes on, it starts talking about ADHD, and then it just starts talking about general stuff that kind of repeats itself and is a bit circular. And the reason why it's done this is because this neural model has been trained on hundreds of thousands of research papers that maybe some of them have actually mentioned a connection between Parkinson's and ADHD. But this particular paper that we're trying to summarize doesn't. So this is talking about, this is generated facts that it's found out about from a large corpus, but it's irrelevant to this paper. Having said that, it's actually an interesting piece of information that it's generated, because it turns out that some researchers do think there is a link between ADHD and Parkinson's disease. So from that point of view, it's pulled out some useful information that you might want to then investigate. But as a summary of the paper, it's not very helpful. It's factually wrong. And recently, some researchers have been trying to fix this. I'm sure you are familiar with some of this new research. So here's an example here of a paper where they're trying to optimize the factual correctness of a summary using radiology reports. I'm showing you the Scholarcy version, if that's okay, if you don't mind, rather than your full paper. This is a really good example, because what they're trying to do here is using typical neural approaches, so using transformers to summarize this radiology report. And you can see that the human summary is 2 sentences: neurothorax is seen, bilateral pleural effusions continue. And the neural generated summary here says no neurothorax is observed. It has a high Rouge score because when you look at the similarity of the individual tokens, there's a high degree of overlap. But it's wrong because they've introduced a no there. So Rouge scores don't always tell you, you shouldn't be optimizing for Rouge scores if the facts are wrong. And here's another summary here that's been done via a different method, probably via an extractive summarization, but oh no, maybe not in this case. But you see, this is factually correct, but it has a lower Rouge score because it's introduced some new words. So you shouldn't always go by the metrics. It's more about, is this factually correct or not? So in this paper, what they're doing is they're saying, well, how can we optimize for factual correct? How can we attend to facts, really? So one of the things we do in Scholarcy is try to do this in a slightly different way, because we're not using a neural attention model at the moment. So how do we, we identify facts first in the content. And this is the same as what that paper I was just showing you also do. So we identify triples using open domain information extraction, which I'm sure you're familiar with, and there's many different ways you can do that. I won't go into the literature on open domain IE because it's, there's extensive literature on that, on knowledge graph construction and so on. But essentially, you're looking for triples of subject, verb, phrase, object, and maybe where the subject is an important entity, carbon capture or Alzheimer's disease or some kind of entity, and then a verb phrase that's not just like is or was, but is an extended verb phrase such as shown to be effective in, or is the primary cause of, or something, some longer verb phrase that maybe ends in a preposition that leads to the object. So if you're not familiar with the literature on open domain IE, then there's a sort of recent paper that is by Sebastian Riedel and Andrew McCallum on this, on using this, leveraging neural approaches to generate knowledge graphs. It's worth checking out. So the first thing we do is identify these triples, and then we also identify claims. What was actually done. So you're going to look for kind of verb phrases like we investigated, we proved, or this study shows, and so on. Try to identify those kind of claims in the paper, and then we rank them in some way, in this case using a graph-based algorithm, attending to the keywords in the triples and the claims, and then simplify the text. So removing phrases like however and in that case, and all these what we call transitional phrases. And then we do the abbreviation expansion that I mentioned earlier. And then really you want to ensure that this stuff then is copied to the output unchanged and that no new entities are generated. So that last bullet point is really what this research is trying to do here, is by identifying triples in the text and entities, then we're trying to fix those and say, okay, then let's make sure that when we're doing this copy operation from the input to the output, we're making sure that that stuff doesn't get changed. We're making sure that these are invariant. And this paper here, where they've done that, is similar to another paper by this team at Salesforce, led by Richard Socher, who was one of the first researchers to really apply kind of deep neural techniques to sentiment analysis, and then he went to work for Salesforce and has been investigating summarization. So they're also doing a similar approach where they identify facts in the text, and then they change the verb in the fact. So they might change, if I could show an example here. That's not really illustrative. Basically, in this paper, they change if I go to the original paper, it might be easier to show that. Let's have a look. Yeah, where are we? It's in one of the tables. Right, if you can see this. So what they've done is, oops, trying to make this bigger so you can see it on screen. So you can see the original sentence that they've extracted. Snow was predicted later in the weekend for Atlanta and areas even further south. So what they're doing is by breaking this down into subject, verb, phrase, object, triples, then they can switch the verb for a different verb. So they use a rule-based approach to transform the data into its negation in this case. So they transformed was into wasn't, or they transformed his into your. And the reason they're doing this is they're using this to generate counterexamples where they want their transformer model to learn what not to do. So they're saying, don't use this as a negative example of a summarized sentence. Don't switch his to your, don't switch was to wasn't. And so by providing these negative examples of bad summaries or bad phrases where you've got a bad transformation from was to wasn't, or a bad transformation from his to your, the system can learn when it's going wrong, basically. So what it shouldn't be doing. It shouldn't be introducing switching entities. So it shouldn't be switching Guy Luzon to Bordeaux, for example. So they're using this to generate negative examples. And this works quite well, but it has a relatively small effect. So I think it improves, makes a sort of 8% increase in F measure, which is good, but it's still not perfect. So there's still some way to go. So at Scholarcy, what we're doing is we're doing the first few parts of this. We're doing the extractive-based summarization, but we're not then feeding that into a neural model. In future, we might do that, but it's really extractive-based because we really wanted to guarantee that whatever we extract is factually correct and can be linked directly back to the source. So here's an example. Here's a paper on weather affecting pain, people who have chronic pain. So things like atmospheric pressure and humidity. So what it's done is it's transformed this paper here into a headline. The study has demonstrated that higher relative humidity and wind speed and lower atmospheric pressure are associated with increased pain severity in people with long-term pain. So we've used this approach here, pulling out the subject, verb, object triples, ranking them, and then pulling out the top one, and that generates this headline. And then the rest of them become highlights. So we take the top 5 or 6 and we generate these bullet point highlights. So this is like a small summary that is over the whole paper has pulled out effectively what could be used as a separate, as an abstract, or as maybe an abstract that has a bit more detail because it has some of the main findings here of the odds ratios and so on. And it's expanded the abbreviation from OR to odds ratio. So if you're a new reader, you don't know what OR means, then it will expand that and you can click on that and go to the Wikipedia page about odds ratio. And then within that, it's got keywords such as relative humidity, wind speed, chronic pain, and so on. So that's one type of summarization where you're basically pulling out the main claims and the main facts, the main findings. And here's another example here, a paper on mentoring for small and medium enterprises. Again, we pulled out the main finding. And this has probably been picked out because within the claims that we identified, this is probably the one that is most rich in keywords. It seems to have a lot of keywords in it. So this may be why. I mean, there's various different approaches that the ranking algorithm uses, and it's not always clear how using the how it decides on a probability basis. This is most likely, but this is probably how it's decided it. And then you've got the other highlights here. So again, this functions as like a separate abstract, if you like, if there wasn't an abstract already. I think actually in this example, because I'll come on to evaluation in a bit later, but in this example, we removed the original abstract. So you can see here that this article goes straight from title to introduction. So there was no abstract for this paper, or in this example of it. And so these highlights could be used to generate an abstract. And in fact, that's how some people are using this at the moment for things like book chapters, pulling out the top 5 points, the top 5 findings, or the top 5 claims, and linking them together into this abstract. So the other type of summarization then we can do is summarize individual sections. So rather than just going over the whole paper and pulling out the top 5 or 6 claims and findings, we can say, well, let's just do one section at a time. So here's an example of a structured summary that's generated using this extractive approach. So we've summarized the introduction into a few bullet points. We pulled out the main objective, and then we've summarized the methods and the results and the conclusion. And again, that can be quite helpful where a paper, you're submitting a paper to a journal and they want a structured abstract. So this could generate that for you, and then you could maybe edit it into, tidy it up a bit. Maybe there's some extraneous information that's not necessary, because obviously this isn't going to be perfect, right? This is going to pull out stuff that's maybe tangential to the point that you want to make, or it could pull out some noise. It might end up pulling out, there might be a figure caption in there or something you don't want. So you obviously want to edit this, but it does try to give you a structured summary with the main sections in there. What we found actually when we've done evaluations of this is that the conclusion tends to come out quite well in the introduction, but the methods and results don't summarize that well, and that can be because often in the results you've got tables in there, so you still need to refer to the table. The methods might be quite long, or they might be in an appendix that so it can be quite hard to summarize the methods as a separate entity. But as a starting point for a structured abstract, this can be quite useful. And then the third type of summarization that you can do is coming back to what I showed at the beginning when I said, we can enrich search results with like a micro abstract. So this is what that looks like here. where we've really kind of cut it down to its bare bones, and so we've removed actually the subject from the sentence and just put in the verb. So we just say this shows that plastic contamination levels are similar to those in the Caribbean Sea, shows that the linear fit and theoretical model estimates for CS when integrated with plastic concentration is equal to this, found that the surface waters of Australia are contaminated with small plastics that are mostly a byproduct of degradation of larger objects, shows that the distribution of marine plastics is quite widespread, patchy and dynamic. So we've really kind of extracted the main findings here and then really abbreviated the sentences as much as we can to focus on the verb and the object rather than the subject, because the subject is really just, the subject of these statements is the paper or the research or, the authors and so on. So we don't really need that, but we're just focusing on what they're showing. And really we're focusing on the object of these sentences here. And the reason for doing that is coming back to the use case, which is when I'm reading the paper and I'm reviewing what the author's saying, it's kind of useful to be able to mouse over this citation, and then rather than having to go and find that paper and switch my attention from one thing to another, it's nice to be able to just see the main findings of that paper in context. So that was the use case for doing that really kind of brief summarization, is into a few short sentences that could fit into this little box, was to have that ability to read the main findings of a paper without having to leave the main paper that I'm reading. So to be able to do that here as well can be a little bit slow, because it's actually going out and finding that paper and then summarizing it while we wait. Obviously, you could think more efficient ways of doing this, but that's how it works at the moment. So we get that there. I don't know if you've come across a tool called Cite.ai, but we've integrated that as well. So you can see how many people have supported that study and how many have mentioned it. Because quite often in citations, people just mention a citation, but you want to know actually, are they replicating the results? Are they contradicting the results? So being able to see the stats around this paper to know, is this a good paper to cite? It's quite useful. So you can actually click on that and have a look there. So this is really cool, Cite.ai, because they've classified all these citations as supporting or just mentioning or contradicting. So nobody's contradicted this paper yet, which is nice. 6 people have supported it. And then you can see the context here. So yes, here we go. Our reported wing mixing factor was very similar to those previously found, and then they're mentioning that paper there. So you can see, yeah, this is a verified verified paper that other people have cited and other people have supported. So that's quite useful to know that. At peer review time, if you're reviewing this paper, it's quite good to know that they're citing legitimate research and they're not just citing something that maybe nobody else has cited, or they're not citing something that maybe is not in a high quality venue. So having these kind of facts at your fingertips to be able to find that out can be quite useful. So that was the motivation for that third level of summarization there. Okay, so how do we create training data for all this stuff then? Because there's lots of steps to this process. There's extracting the text, cleaning up the text. There is then classifying each line of text according to its semantic function in the document. It's quite hard to get training data for this stuff for scientific papers. So how do we do this? So one way you can do this is using this tool called Snorkel. And this is really cool because what it does is effectively lets you write rule-based labelers, which you write a number of different labelers, and it tells you which ones are contributing most to your classification and which ones are maybe contradicting or overlapping. So it's a way of basically bootstrapping a rules-based approach to build a model, and you can choose which type of model you want. So whether you want simple logistic regression classifier or something more sophisticated. So here's an example of a labeling function. So what I've done here is I've just said, okay, for each of my sentences, I'm going to extract subject, verb, object triples into a function that is trying to decide whether this sentence is a finding or not a finding. So in this really simple example, I'm not suggesting this is how we do it in practice, but this can be a useful starting point. We basically say, if we've got a bunch of entities, so we're using Spacey's entity extractor here, so we've got all our entities in our document. So we're saying, is our first entity in the subject, and is our predicate in one of these verbs? So is it something like saying causes or demonstrates or finds or shows? If it is, then this looks like maybe a finding that is interesting, so I'm going to label this as true. Yes, it's a finding. If it's not, then I'm going to abstain, which means we're not going to say it's not a finding, but we don't have enough information to know. So imagine we have a bunch of these labeling functions, each with a different type of rule in it that you've decided. So we might have, say, 3, 4, 5. So you tell Snorkel all your labeling functions, and then you apply this filter, and then you apply it and you create a model from it. This is kind of boilerplate text that's in the Snorkel documentation. And then it's going to apply labels. So it's going to apply the label of true or abstain or false if we've got a false labeling function, and it'll build a model for us, which is great. And then we can see how well that does. So we could then maybe manually correct our training data and see how well our model performs, and then reapply that model. And this is a really quick way of building a classifier where all you've got is rules, or you don't want to have to manually label all this stuff, so you want a quick way of labeling it using heuristics, using your own domain knowledge. It works very well. So how did this do then? So we had all these different techniques, as I've shown, to create summaries. How does it work? How well does it work? So we did an evaluation with some subject matter experts with 125 papers across 5 domains. So we had engineering, humanities, life science, medicine and surgery, and physical science. And what we did was we asked them to rate each of the summary types that Scholarcy generates. So rate the main headline. So just to recap, that main headline is this bit here, the main finding, if you like. Rate the highlights, so rate these bits that are generated here, these top 5 or 6 bullet points, and then rate the longer summary, the structured summary that's generated on a scale of 1 to 10 for salience. So, how central is this extracted sentence, or this summary sentence, to the paper? How relevant? So it could be relevant, but it might not be necessarily central. It might be, it's quite a useful summary to pull out, but it's not the central fact. So relevance and salience, and then consistency. So consistency means that, how well do these statements flow? So coming back to here, does the second sentence naturally flow from the first, or is it really disjointed? So this is what they did. So there were 3 independent subject matter experts looking at all these papers, and it was single blinded. In other words, we didn't know what papers were being chosen. We had no knowledge of what they were going to select, and it could have been a Word document, it could have been a PDF. We didn't get to see this at all until they presented their results. So we had no opportunity to tweak or, say, oh, well, hang on a minute, can't we just fix it just for this? No, we didn't get that chance at all. So it was a good evaluation of a real world use case in that case. So we can see that for physical science and medicine and surgery, it did quite well. We were getting ratings of about 7.5, 8 for all of these. From the headline, from the highlights, from the structured summary, and from the keywords. But we did quite badly on life sciences, so biology and genetics and so on. Well, it's not too bad. I mean, we didn't score lower than 5, which is good, but you know, it wasn't great. We did a bit better on humanities and a bit better on engineering, but certainly in physical science and medicine and surgery, it was pretty good. So we were happy with that. But there's obviously, you can see there's more work to be done on these 3. On the other hand, I'm quite happy with these results because we were using completely generic techniques for this. You know, as I say, we use open domain information extraction, we use graph-based ranking, we use unsupervised keyword extraction. So it's not been trained specifically to look at, you know, only train on physical science or only train on humanities. It's, you know, looking at a range of papers, and a lot of the techniques we use are, as I say, are unsupervised. There's just the main supervised part of Scholarcy is on the classification of the semantic function of each line of text. You know, is it an abstract? Is it a heading? Is it a paragraph? Is it the title? So is it a finding? Is it a claim? But we don't know about, you know, what subject domain it belongs to. We're not really actually interested in that particularly, because we're interested in making this a more generic thing. So it's actually, you know, we're quite happy with that. But obviously there's something going wrong in life sciences that we need to figure out. And this could be because of what I was saying earlier about summarizing methods is quite hard, particularly in things like genetics, where they've actually got a long series of steps that they take, and a lot of this methodological information might be in an appendix or supplementary data anyway about, you know, they did the Western blot analysis and all this other stuff. And humanities is notoriously hard to summarize because often this humanities stuff is things like biographical information about people. It's to do with rhetorical arguments. It's very discursive. It's very narrative. It's less focused on hard facts. It's more about opinions and exploring and looking at, you know, comparing two arguments and so on. So this is quite hard to summarize that sort of stuff. Engineering, very unfamiliar with the engineering domain, so I'd have to look a bit further about that. The keywords were quite good, so that was useful, but yeah, the summaries weren't so good. So that was really useful, and then we're going to hopefully feed that back and improve that. That's really the end of the main presentation. I'm happy to talk more about some of the detailed aspects of that. I say the main thing we want to do in future is maybe use more neural techniques to do abstractive summarization, to provide that as an option. But we've still got to figure out, you know, how to really make sure that the abstractive summaries are factually correct, which we can guarantee when it's extractive summarization, but we can't guarantee it when it's using a generative model that's going to, you know, generate new content. So that is the major challenge for abstractive summarization at the moment. And as we saw with papers like this paper by Krasinski and others, this is a key area of research for recent research is looking at how to guarantee that factual consistency. Because if we can solve the factual problem, then abstractive summarization becomes viable to use in the real world. It's not just something that, you know, you play around with and have fun with it. You know, in tools like Write with Transformer, which you've probably seen, it will generate some text for you. You want to make sure this is actually consistent and correct. So if we can crack this problem, then, you know, we're there really. But I don't know, you know, obviously to crack it completely, we're talking about artificial general intelligence, which is still a long way off. But, you know, maybe with a specific domain like news, we can try to at least solve it. I don't know if we'll solve it in the scientific domain, but, or I'm not even sure how useful abstractive summarization is with scientific articles, really. I mean, the main use case would be for something like generating a lay summary. So, you know, if you wanted to, let's have a look at an example. If you're a lay reader, you might want to, if the paper's written in quite a dense way, which luckily this one isn't, but you might want to know what some of these words mean. And so our approach to lay summary generation is to say, well, look, can we just take the terminology and just generate a summary again from Wikipedia of what this terminology term is about. So, you know, is that enough for a non-expert reader? Is it enough for, you know, somebody, if we extract the main highlights and then we just provide a way for someone to go to Wikipedia and read, you know, more about what the shikimate pathway is, for example? I don't know is the answer to that question, because if we were to generate a lay summary of this highly technical paper, yeah, there we go, it's done it now. It would actually be quite big, because you'd have to explain about this pathway, you'd have to explain about this thing here, ESPS, and, you know, it's kind of hard to know where you would start. So, you know, maybe it's enough just to say, well, what an opportunic pathogen is, or what gut microbiota are, or, you know, what glyphosate is, and so on. So that's the approach that we take for making this accessible to a lay reader, is providing these links. And that's the purpose. You know, that's going to be a separate evaluation, really, to to see if providing Wikipedia definitions for terms like this is enough for a non-expert to understand what's going on with this paper. But in future, you know, having that automated into an abstractive summary could be the way forward. Great. So thank you very much. Thanks for listening. I hope that was useful.
Thank you, Phil. So we have a few minutes to have a couple of questions from our researchers. So the first question goes as like, what is your take on citation-based summarization of research articles? Because we see few papers coming up on those areas. So yeah, if you can say something.
Great. That's a really good question. Thank you. So citation-based summarization is where you summarize the you look for the context around a citation. Is that right? So if I share my screen a bit, maybe again, you can look at an example. So so would this be an example here? We've got a citation here, 13 to 15. And so we would take that sentence as a candidate for our summaries. Herbicide is known to affect the growth of microorganisms. Is that correct? Is that the sort of thing you're thinking of?
Yes.
Yeah, I think that's a good idea. Funnily enough, I don't know if you can see this, it's been highlighted in yellow by Scholarcy. It seems to have automatically done that anyway without being told. Just using the fact extraction engine, it's highlighted that stuff, and there happens to be a citation there. I've looked at this briefly. I must admit, I wasn't convinced. When I did actually run a test, although we didn't really formally evaluate it, and so we did pull out all the citation contexts. The question, I suppose, the thing is, you're going to get, you know, in a long paper, you're going to get a lot of these sentences, and most of them are probably going to be in the introduction and the discussion, aren't they? Because most of the citations will be in the introduction, the related work, and the discussion. You're going to miss out maybe the stuff in the methods and the results, potentially, because you won't have a citation in there. So that's one risk. The other thing is that, you know, in some papers with a lot of citations, this only has 47, but, you know, some papers will have hundreds of citations, like a literature review or systematic review. So then you've got to find a way of ranking them, haven't you, and deciding which are the most important. You could say, well, I'm only going to use the ones in the introduction and the discussion. So yeah, it's a valid approach. I haven't really looked at it in detail. I'd say I've done a few tests, but I wasn't really happy with it. I don't know, what's your take on it? What do you think?
I guess you are asking, right? So
I want you, apart from the citation based summary, what are the other methods that are going on in the
Okay. So yeah. So Phil, I have one question regarding. So I was working on semanticizing the research paper. So I believe that you have not started working on the deep neural architectures for summarization. But any your take on that? How could we produce better semanticized version of research papers, considering that there are many entities like the mathematical equations and some references which are pretty old and not parsed correctly by the current parsing engines. So what is your take on that particular thing?
So your question is, how do we deal with mathematics?
Mathematical equations, yeah.
And older references that don't get parsed correctly. Yeah. So, well, for mathematics, I don't know if you come across this tool called MathPix that allows you to take a photograph of an equation or drag over an area in a PDF that has an equation, and it will convert it into LaTeX. Have you seen that?
No, I don't know.
Oh, it's cool. Right, so check that out. I'll put it in the chat. If I put this in the chat, will you see this? It's called mathpix.com. So they have an API. So if you could figure out the bounding box of equations in a PDF, for example, then you could potentially run them through MathPix and convert them to LaTeX. So that's one way of dealing with equations. I'm not really doing that right now. I'm trying to kind of. I'm not trying to. I suppose my goal is to try to distill a paper into its main findings and arguments. I'm not trying to reproduce the whole paper in its entirety and turn it into a semantic representation of the whole thing. So if you wanted to do that, then yeah, equations are important, and something like MathPix could help you. So it's worth looking into that. You've still got that problem of identifying the bounding block of each equation, but once you can do that, then you can use that. On the older references, are you thinking about like papers that are only available as scanned PDFs that don't have that need to be OCR'd, or which, have you got an example you can think of?
Yeah, so papers mostly like the papers before 1990s. So mostly those are in scanned forms, and yeah, so the current parsing engines could not produce the editable versions of those. So
what are you using to parse references at the moment?
so at this moment we are using Grobid and ScienceParse.
Oh, okay, cool. Yeah. So something I forgot to mention actually in the introduction, one of the motivations for Scholarcy as well, I'd use Grobid and I'd use Sermine. Have you come across Sermine as well?
Yes.
Yeah. So
yeah.
That's it. And ScienceParse. The problem with all these is they had quite big memory requirements. You needed at least 16 gigs of RAM, maybe more. Certainly for ScienceParse, I couldn't get that running on less than 24 gigs of RAM, and Grobid needs 16, and Sermine needed a similar amount. I wanted something that I could run in quite a low memory footprint, and I wanted to. Also, I love Python. I wanted to write something in Python, so that was the motivation for that partly. Grobid is pretty good. One of the problems I found with Grobid is that it's not very good at extracting. Let's just look at an example. May I share my screen again, if you don't mind? Right. So one thing Grobid's not very good at is getting rid of these headers and footers from the PDF. So one thing I found when a paper like this, Grobid tends to keep this stuff in there. So if you're in the middle of a references section, Grobid gives you all this stuff as well, which you don't want. So for me, that's quite important. I don't want that stuff in my references. So it's important to be able to screen that out. So that was one weakness with Grobid I found. It does do a pretty good job of references, but we actually had to deal with this challenge actually when we did some work for the British Medical Journal. So actually, if I can just show you the blog post we write that, I can find it. Yeah. So because we had exactly that problem, we had I'll send you a link to that if you want to read that, and I tell you a bit about how we solved that. Well, we didn't really solve it. We tried to solve it. We partially solved it. So I don't know if can you see that blog post on there, but this is exactly the problem you described. They'd had all these scanned PDFs, so the PDF looked like this. They'd OCR'd it. So the first step is you've got to OCR the text. And some of these PDFs dated back, you can see 1975. We actually had some from 1840. And so when you OCR it, you get, as you probably know, you get the text looks, if I zoom on this, can you see this a bit better? Sorry, because it's a bit small. there's the scanned image of the references. Here is the OCR text. Can you see that on your screen?
Yeah.
Yeah. So you get text like this, don't you, from the OCR? It comes out like that. It's all kind of squashed together, isn't it? Or it's kind of split up. So the first thing we had to do was write a rules-based approach to try to, first of all, to try to figure out the line, rejoin the lines together, and choose a different PDF engine. So we experimented with a few. We used PDF to text from XPDF. You probably used XPDF, haven't you? Use that. Poplar, as I mentioned. So some of these are quite good at pulling out cleaner text, so you actually get the spaces correctly, because sometimes you have everything just joined in one word. So something like Grobid might give you this, but if you try XPDF or Poplar, you tend to get cleaner text. And then what we were able to do by using these tools instead was to get nice clean XML out, you see. So we were able to actually get the structured and unstructured citation with all the nice spacing and correctly separated out. So the way we did that, using these two, XPDF and Poplar, and then we ran it through any style parser, which we retrained. So I suppose putting my commercial hat on, I would say if you want to do this, just use our API. Now, this API actually is free to use for reference extraction. So up to 50 papers a day. So, you can, I can just show you this actually. So if I, where are we? If you go to ref.scholarcy.com, you can either upload a paper or put in the URL. And if I extract BibTeX, it will do XML as well if I run this. Execute. Let's see how well it does. Okay, so let's just download that. I'm going to open it in. It's automatically going to open up the BibTeX in Zotero. There we go. So it's done quite, as you can see, it's done quite a good job of parsing it, but that's a new paper, that's not OCR. So yeah, what you could do as a baseline, if you want to build, if you're building your own, see how well ref.scholarcy.com does on that content first. You are still going to need to OCR it though. You have to have text inside the PDF. We don't do OCR automatically, and I think that's probably the most challenging bit, is to get clean text out of your PDF. If you can solve that problem via OCR, then the reference parsing bit is more straightforward. So use a good OCR engine, which at the time we didn't have, so we had to use heuristics to clean up the text and run it through XPDF and Poplar. But yeah, there's no real solution to that, unfortunately. It's going to be a bit hit and miss. Sometimes you're going to get good results, sometimes you won't.
Any questions?
So you are mentioning about 3 techniques for summarization. In the summarization 1, are you considering all the sentences of the document or a subset of that?
Sorry, am I considering?
You mentioned about 3 summarization systems, one micro, another section-wise summarization, and one is a document. For a single document, you are producing one summary. The first summarization 1.
Yes.
So in summarization 1, are you considering all the sentences present in the document or a subset of that?
There is some filtering going on. So we've already removed, for example, the references. We've removed the metadata, so anything up to the abstract. We're not looking at any appendices. So really what we're looking at for the full document summarization is the text that occurs from the end of the abstract to the beginning of the references, and we then do that. And then we'll maybe clean it up a bit more, so we'll try to remove any tabular text. Sorry, I was still screen. I didn't realize my screen sharing. Sorry about that. Yeah, so we try to remove tables as well, figure captions. So we clean the text up, but yeah, basically it's that section from the end of the abstract to the beginning of the references. And then if we want to do a structured summary, then we summarize each section separately. So we summarize the introduction separately and the methods and so on.
figures are you considering? Figures?
No, no. We extract the captions, but we don't include the figures in the summary. So we extract the figures separately into a separate block within that summary card. If I may share my screen again, just to show an example. So you see here. So this is what this is the rendered HTML rendered version of the JSON data that is generated by Scholarcy, and you see we've got the figures in. We did have the figures. It seems to have gone. Let's try a different version. Sorry about this. Yeah, there we go. So we got the figures in a separate bit. They don't form part of the summary. They're available if you want to view them, but we don't summarize the captions. It's just anything that's not a caption and not a reference, and anything that's part of the main body text, basically.
Okay. So
I don't know how would you summarize figures though? I mean, how would you do that?
How to summarize figures? Like, what is it?
Okay, so maybe you can extract the sentences which are referring to the figure. So we are working on this figure assisted summarization. So from the text, we are finding out those sentences which refer to the figure.
Oh, good
that
point.
That is the set of base sentences.
Gotcha. Yeah, that's a good idea. Never thought of that. And maybe for tables as well, like here, for example, where it mentions table 1. Maybe that.
Yeah. So table 1 is referred by multiple sentences. So maybe you can summarize those sentences to get an idea of the description of the sentence.
That's a good idea. Oh, great. I'll be interested to see the results. So
yeah, another question. So in your sequence to sequence model, are you giving the sentences as input or a document vector as an input? So yours is abstract summary. So there is a sequence to sequence model. So are you giving the sentence vectors as an input or a document vector as an input?
So we're not doing abstractive summarization. I talked about it, but yeah, we're not actually doing it. It's at the moment, this is all extractive.
Oh, okay.
So it's ranking. Yeah, the input is a sequence of sentences, and these are ranked and simplified. But yeah, we're not doing any sequence-to-sequence summarization right now. It's on our plan to do this, but we're getting quite good results from extractive summarization. So in future, we'd like to do that. I think we're constantly focusing on cleaning up, getting as clean text as possible. As you can imagine, getting clean text out of the PDF is quite hard. So if we can really get that as good as possible, once we're really happy with that, then we'll be able to filter that more efficiently, and then we can use abstractive. But yeah, the input to an abstractive summarization would be sentences that have been selected and cleaned beforehand. I think, as you probably know, 80% of the work is cleaning your data, isn't it? It's getting decent quality sentences and decent quality text before you process it. And we're still spending a lot of time on that, to be honest.
Thanks.
Thank you. Thanks. That's great. Yeah, it's a good idea about the figure context. That's a good idea. Yeah.
So I guess there are no more questions. So we thank you, Phil, for this talk, and we will post this in our website as well, and we will send you the link. And thank you for your time once again.
Great. Thank you. Would you like a copy of the slides?
Yes, we do.
Okay. They're quite. I'll put them on Dropbox because they're about 22 megabytes, so they're quite big because they've got images in them. But I'll stick them on Dropbox. I'll send you the link, and you can host them.
Sure. Okay. Thank you.
Great. Well, thank you very much. Good to meet you all, and I look forward to reading more of your research. And let's keep the conversation going. So thank you very much for inviting me.
Thank you.
Bye-bye.